The United States, where we're very concerned about greenhouse gas emissions, uses about 20% of the world's energy today. So if we were to cut our CO2 emissions to zero, we'd still have to worry about the other 80%. And the other 80% is growing at a tremendous rate as these nations develop. So we'd have almost no effect of zeroing our own CO2 emissions. Not only do we need to have a source of energy that is CO2 free, we must also be able to export it and install those kinds of power plants in all the nations around the world. And the only way to do that is to make them inexpensive enough that all the nations of the world would rather have them than their existing coal plants. Today we have just left Los Angeles. Hi, I'm Robert Hargraves. I'm on a plane flying to Shanghai International Thorium Energy Organization Conference being sponsored by the Chinese Academy of Sciences. This organization is actually planning to build a thorium molten salt reactor, so we're really excited to go to the presentations and see what's really happening there.
And why are you headed there?
Well, I'm headed there to give a talk. My new book is called Thorium, Energy Cheaper Than Coal. And it is my thesis that this is a nuclear power plant that could actually deliver electrical power less expensively than coal plants. The objective has to be to keep that price down, because that's the way we can persuade all the nations of the world to stop burning fossil fuels. In the long run, people always do what's in their own economic self-interest. First, let's start with coal. The US EPA says coal causes 13,000 deaths a year from respiratory disease caused by particulate inhalation of particles of about 2.5 microns or less. That's in the US alone. In China, over 100,000. The UN estimates in the world, almost 1 million people die from coal particulate emissions. One of the problems with global warming that I find the worst is the lack of food and water caused by the melting of glaciers. Glaciers normally retain water in winter and release it in summer, but the rivers that are fed by the Rungbuk Glacier are now becoming less able to provide water during the summer. Without water, growing food is next to impossible. Population growth depletes food. Since the 1950s, 90% of the large fish in the ocean are gone. Resource competition can also lead to war. In 1990, these are the oil wells that were set ablaze by Iraq in Kuwait. So if we did not have quite so much resource competition, we would reduce the impetus for war. Let's look for a minute at prosperity and population. These are data from the US Central Intelligence Agency. Each dot represents a separate nation. On the horizontal axis, children per woman. On the vertical axis, GDP per capita. Nations with the most births per woman are really the poorest ones. Population scientists say about 2.3 children per woman leads to a stable population. And if we just draw that on the graph and look at it, it's the wealthier nations that have a stable or reducing population. The United States birth rate is about equal to that would cause no growth. US population growth is principally by immigration. So how can we fix this? Well, let's look at prosperity for a second. I arbitrarily defined prosperity to be about $7,500 per year. That line seems to differentiate pretty well between those nations that have stable populations and those that have growing populations. Interestingly, that's about the same GDP per capita as China is today. Prosperity depends strongly on energy. Again, CIA data, annual kilowatt hours per capita. The US is off the charts at about 12,000 per year. That's an average energy consumption rate for electricity in the US of almost 1,500 watts on average. Places in Africa have electric consumption of less than 100 watts per capita. It's pretty clear that somewhere around 2,000 kilowatt hours a year is the break-even point for achieving prosperity using electric power. Now, electric power is not the only way to achieve prosperity. You need education, property rights, rule of law, medicine, and so on. But electric power is critical to prosperity because it's the type of energy that is necessary for cooling, for heating, for water purification, for sewage processing, for medicine, for communications, for industry, for transportation. All those things depend upon electric power. All the developing nations know this. They wish to increase their energy use. And so you see, the non-OECD nations are projected to have the most growth in energy over the next few decades. How are they going to do it? They're going to do it by burning coal, because they don't have money to build $5 billion nuclear power plants. They will use the cheapest energy source available to them because they desperately need that electric power. Now, carbon taxes. Carbon taxes are not an adequate solution. Here's a man, Jeffrey Sachs, who was the leader of UN Millennium Development Project. He was also the financial advisor to Poland, to Russia, and so on. He's a well-known economist, and he says taxes aren't enough. We need a new technology. And not only that, we need to have that new technology spread to the whole world rapidly if we're going to have any effect. The China Daily in 2010 published this little article. Technology is required to solve this problem. They also argue against carbon taxes. Here's that same chart magnified. They point out that cumulatively in the US, we are responsible for about 1,000 tons of CO2 per person, whereas in China, it's less than 10% of that. And so the developing nations argue that the West gains its prosperity by cheap energy, by burning coal and emitting CO2, and so why should the developing nations be denied that right? It's not fair. I'm not trying to make the argument, I'm trying to point out that it's impossible to reach agreement on such a contention. So we tried anyhow. We had conferences in Kyoto, in Copenhagen, in Durban. You know, 30,000 people went to the conference in Durban to negotiate a climate treaty. Well, how can 30,000 people agree on anything? How can 7 billion people in 250 nations in the world agree to impose taxes on carbon that is against their individual economic self-interests on behalf of the whole world's stability? It's not going to happen. So let's look at the cost of electricity from coal and other sources, because there's also a green movement that wants to replace coal. Here's the cost of coal. About $2.8 per watt of generation capacity is the capital cost for coal. In this talk, I use a single model throughout, and I use the financial idea that if you do capital cost recovery at an 8% cost of capital over 40 years, operating a plant 90% of the time, you get 2.8 cents per kilowatt hour. So it's easy to remember, $2.8, 2.8 cents. So that's the capital cost. The fuel cost for coal is about $45 a ton delivered to the plant. So that adds about 1.8 cents there. So in this model, the cost of coal for a typical US plant is about 5.6 cents per kilowatt hour. Now people are saying, well, we have better technologies like integrated gasification, combined cycle gas plants. These are coal plants that burn coal in oxygen rather than air, so that the effluent is only water and CO2, so the CO2 can be extracted. But only one of these plants has ever been built in the US. That very pretty picture is the one in Florida. And it's expensive. Natural gas is another interesting energy source. First of all, if you were going to do the best job you could, you would use a combined cycle gas turbine, which has a 60% efficiency of conversion from thermal power to electrical power. Buying such a thing costs about $1 per watt for capital costs. I used fuel costs now at $5 per million BTU to come up with a fuel cost per kilowatt hour of 2.8 cents. Our operations costs are standard in this model, and that comes to about 4.8 cents per kilowatt hour. Now, on the other hand, the cost of gas right today is a little lower than that. And if that were to persist forever, we could have a low cost of power from natural gas of only 3.7 cents. But actually, we don't use combined cycle gas turbines very much. We only use natural gas combustion turbines. And that would mean it would be about 7 cents. So those are the bogeys we want to deal with. Here's the reasons that natural gas prices will rise. Here's the prices of natural gas worldwide. In Louisiana, about $3. In Japan, about $16. Japan is importing liquefied natural gas more and more because they've shut their nuclear power plants down. And it has changed their balance of trade from a positive number to a negative one. So that really can't persist for long periods of time. Substitution. Just look at the price per BTU of energy, thermal energy, from oil versus natural gas. There will be substitution. There'll be more emphasis on flex fuel vehicles. So that's going to drive up demand for natural gas and raise the price. Even the Energy Information Administration of the United States says that it's going to go up. That's why I used $5 in my model. Let's look at wind. Wind is integrally tied with natural gas. This number is pretty high, isn't it? Well, the reason is that it costs a lot of money to build these wind farms. It's very hard to find the right costs. The costs are generally hidden from the public, so the public doesn't know the subsidies. But here are two examples. Deep water wind off the coast of Rhode Island, Cape wind off the coast of Cape Cod, Massachusetts. These are the costs per watt. But those capital investments can only be recovered in the 30% of the time the wind is actually blowing. So the capital cost per kilowatt hour generated is much higher. It's 17.4 cents. Now, the fuel cost is nicely zero. The ops cost, I made the same for all of this model. I got 18.4%. I checked that against the real costs, and Cape Wind has negotiated a deal with the state of Massachusetts in which they will sell power at that price. So I say that model's about right. That's how much it really does cost, but they're going to hide that number from the ratepayers. Now, wind turbines increase CO2 emissions. How can you say such a thing? Let me explain how. First of all, if you had hydropower available, you could use hydropower to back up the wind turbines during the lulls. So if the wind turbine is running 30% of the time, the hydro could run 70% of the time. In most situations, there isn't enough water to run hydro constantly, so you only open the floodgates to run the turbines when demand is high. So if you had wind turbines coupled with hydro, you could in fact just save water in a sense, not emit more CO2. That's a good pairing. That's the kind of pairing that's done in Denmark with the hydro facilities in Scandinavia. But I want to go back to the two kinds of natural gas turbines. The most common one is a combustion turbine, much like a jet engine. It is only 29% efficient in its conversion of thermal energy to electrical power. But it starts up quickly. It starts up in 10 minutes or under, approximately. So as the wind lulls, the natural gas combustion turbine is used to fill in the gaps. The most efficient gas turbine is combined cycle, and that has a 60% efficiency, twice as good. But takes a long time to start it up, almost an hour, because not only does it burn gas, but it also has to run the boiler with the output of the turbines. So it's a little more expensive, slow to start up, but a lot more efficient when it's running. So let's suppose for a minute that we were planning the energy economy of a nation, and we said, we have a choice to make. One choice is, for a 1,000 megawatt power plant, let's use wind turbines with natural gas backup. Okay, if we do that, then 30% of the time we're not using any fuel, but 70% of the time we're using fuel at a rate of 2,400 megawatts thermal. Okay, Suppose I had only combined cycle gas turbines. Well, I'd be running at 100% of the time at 60% efficiency or less fuel. So I deplete my resource less rapidly, I emit less CO2 by not having installed any windmills to begin with. Let's look at solar electricity. Capital cost, again, very high. Here are examples. These examples are usually hidden from the public. Every once in a while I find a news article that gives the true total cost of it. The costs are not revealed because people are embarrassed about the deals that are made to get subsidies to build these plants. These are the real costs for BrightSource, for Abengoa, and so on. So that leads to 22 cents, more or less, capital cost. So solar power, about 23 cents. Is that right? Well, here are some examples. Albiasa, in a Spanish company that's building such a plant in Spain, 35 cents. All Earth, a US company building one in Vermont, 30 cents a kilowatt hour. So those are about the right numbers. The public isn't aware of them because they're hidden, they're averaged out over the whole bill. But what's important to society is not who pays, whether it's the taxpayer or the ratepayer or an unlucky investor like the government of Spain. What matters to society is the true cost. So let's look at those, and that's why we're doing this. Biomass. The cheapest way to use biomass is to burn it. We can talk about ethanol-powered engines and so on, but there's a lot of energy lost in the conversion of the biomass to ethanol. So let's just burn it. That'll give us the best answer possible. Well, capital costs, I looked up for a few plants. I used $4 per watt to build a wood chip burning power plant, and I actually visited one. Capital cost recovery, you see 4 cents per kilowatt hour. Fuel, you have to drive trucks around to the woods to cut lumber and haul it back to the plant, cut it into chips, and burn it. And here are the typical costs. I convert those costs in tons to BTUs times the efficiency of the plant, about 9.7 cents per kilowatt hour. Now, you might say, how do wood plants actually make money if they're selling it so expensively? Well, there are all kinds of, again, rules in the United States, at least, about getting green energy credits that are marketed, renewable energy credits, to make it possible to do that. So, if we want to save the world by underselling coal, here are the numbers we have to beat. And we might have to go as low as 3.7 cents for gas if, in fact, the gas prices never do rise. That's the bogey. That's our objective. Undersell those numbers. Can we do it? Everyone in this room probably knows already how one of these liquid fluoride thorium reactors works. In this example, it's a two-fluid reactor that is fed simply by thorium, and it's sort of idealized, and it continuously processes the nobles, which are relatively easy to get out, and the fission products, which are harder to get out. Weinberg thought that the world's future depended upon such an inexpensive energy source. Weinberg himself wrote about global warming from CO2. There's an intermediate step that could be equally effective, a lot less expensive, the denatured molten salt reactor that actually does not bother to process the dissolved fission product fluorides, but simply leaves them in the salt for 20 or 30 years until eventually they has to be reprocessed or perhaps just dumped and started all over again. In this example, it's fed with U-235, probably diluted in U-238 at a 20% level, and that works. Oak Ridge built one of these without the U-238. They ran it on U-235. They ran it on U-233. The advantage of U-238 is that this kind of reactor is probably the most proliferation-resistant reactor that you could scheme up. Wow. Can thorium energy be cheaper than coal? That's what I want you to learn. The answer is, here are 7 proposals over the years to build molten salt reactors. And you can see $2 is a reasonable number for a target. These are real proposed numbers, inflated to current dollars. The reason this technology is potentially inexpensive isn't the thorium so much, it's the liquid fuel form, because it has excellent heat transfer, allows continuous processing for fuel additions and efficient product removals. It's an atmospheric pressure liquid, so containment is much simpler. And it's a room temperature solid, so if there's a problem, the particulates or the fission products and so on don't necessarily escape so easily into the environment. The safety systems also contribute to the low cost. The reactivity is stable, makes it simple to control. It's a thermal reactor, unlike a fast reactor. There's no meltdown concept. It's as hot as it's going to get. There's no propulsive pressure to push reactive materials into the environment, and so on. There's no large containment dome. That saves money, saves mass. Let's look at the waste product for a minute. Here's the process for converting U-232 to U-233 by neutron absorption in a nuclear power plant, in particular a liquid fluoride thorium reactor. And if you were to let that go, eventually, by more and more and more neutron absorptions, you could actually get up to plutonium-239 and perhaps the higher level actinides. But compared to a normal light water reactor, it takes 6 more neutron absorptions, so it's much, much less probable to generate any of that long-lived, high-level transuranic waste. On the other hand, if you had U-238 in the mix, okay, that's 1 neutron absorption, and there you go. So that's the difference. These kinds of reactors, if you leave the actinides in solution, can slowly get rid of them by absorption and potential fission. It's not as good as a fast reactor, but such a reactor can consume much of its own actinides that are created. And the end result is, although the fission product waste for all kinds of reactors is about the same, and it has to be dealt with very carefully for 200 or 300 years, the long-lived actinide waste, at least from a liquid fluoride thorium reactor, is about 10,000 times less. Another advantage, high temperatures means that you can use closed cycle helium-Brayton gas turbine cycle with an efficiency of 45% compared to a normal power plant efficiency of 33%. This means a lot less energy has to be discarded into the environment, which means cooling costs are lower. You can even use an open cycle Brayton system where you don't have any cooling water available at all. The efficiency drops to perhaps 40% for that. There's a new technology that may beat both of those, and that is the supercritical CO2 cycle with a 45% efficiency at reasonably low operating temperatures. And you can see on the diagram, the little red turbine on the bottom is meant to represent the expected mass of the supercritical CO2 cycle. So that's another reason why this can be less expensive. And of course, thorium fuel itself is pretty inexpensive. Here's a 1-ton ball. That's about the right size of it. You could put it on your pickup truck. You could run the city of Boston for about a year. You could run the entire US on 500 tons. The government has 1,500 tons in storage, just sitting around in the desert. There are millions of tons available worldwide, and there's enough thorium in every country that each country can be guaranteed some level of energy security. They can't be blackmailed by saying we won't give you the fuel. It's pretty inexpensive. Let's look for a minute about the idea of mass production of small modular reactors. My model here is Boeing aircraft. They can produce a $200 million unit every day. And aircraft manufacturers have the same responsibilities as nuclear power manufacturers. They worry about corrosion, material fatigue, they worry about quality control, CAD, CAM, computer-aided manufacturing, all those kinds of things. Why can't we produce nuclear reactors the same way? Then we get the benefit of what's called the learning curve in manufacturing. This is not a theorem, but an observation that every time you double the number of units produced, the average cost drops by something called the learning ratio. In the early aircraft industry, it was about 20%. In the IT industry today, it's about 50%. The University of Chicago postulated it would be about 10%, which is pretty conservative, for the nuclear power industry. That's if we do mass production of essentially the same units. So look at that. We can drop the cost to, 60% or so after 1,000 units of production. So I say, learn to develop small modular reactors at about $2 a watt, about the cost of an airplane, $200 million. Make them affordable to developing nations that can't put in a $5 billion reactor. We can use small ones near cities. We can gang them together for bigger power stations. We can allow them to be truck transported. If we do all that at $2 a watt, the cost of fuel is nothing. I use the same number for operations as before. We can hit 3 cents per kilowatt hour, and we can undersell all the competitive technologies. If we do this, then we can create a new industry. I'm advocating about $1 billion investment in the development stage for R&D that becomes public domain, another perhaps $5 billion of industrial investment to develop the production capabilities, and then the process of producing and exporting one a day. What if we do that? What will happen to the CO2 emissions? We could eliminate in 38 years all the coal plant emissions, all of them. All we need to do is produce one a day. Having solved that problem, what do we do about fuels for vehicles? With only 650-degree heat, we can get about 45% efficiency, conversion from thermal energy to chemical potential energy for burning hydrogen. There are actually hydrogen cars available. The Honda Clarity can be purchased in Florida today if you live near one of the dozen or so hydrogen fueling stations. So they do exist. Ford Motor Company did an internal combustion engine with hydrogen. But hydrogen is not an easy thing to deal with. For one, you have to compress it or liquefy it in order to carry it on board a vehicle. And when you do that even, it's not nearly as energy dense as these other kinds of fuels. Ammonia, methanol, which is a gasoline substitute, or dimethyl ether, which is a diesel substitute. So let's think about carrying that hydrogen with carbon and nitrogen. First, look at ammonia for a minute. More than 1% of the whole world's energy is used to make ammonia. It's used principally as a fertilizer. A third of the lives on Earth depend on food that's grown from ammonia produced this way. And it's produced now from natural gas. But we can also use ammonia to fuel an internal combustion engine. This is a University of Michigan experiment. There's a guy in Canada who has a car that runs on this. It's certainly possible. You can even use ammonia to run fuel cells. These solid oxide fuel cells are sort of laboratory scale now. There's no industrial capability to do these kinds of things. And ammonia really can be handled safely. People say, oh, it's poisonous. Well, gasoline is explosive. You have to look at what all the risks are. And here's some examples. We'd have to pressurize it to about the level of a propane tank. Natural gas and hydrogen are pressurized to much higher levels. There is a spill danger, but you can smell it. It's difficult to ignite. It is toxic, so you don't want to breathe concentrations of it for a long period of time. There's no low-level toxicity risk because the human and mammalian cycles naturally excrete urea. It is toxic to fish, so you have to be careful. There was a report done in the Midwest comparing the risks of ammonia and gasoline fuels, and although they're different, they're about the same. Now, we can make ammonia from solid-state synthesis. It works kind of like that solid fuel cell in reverse. Again, lab scale. NH3 Fuel Association did some papers on this. They estimated, and we adopted it, about 6,800 kilowatt hours of electric power are consumed per ton of ammonia produced by this process. It helped a little with extra heat. Suppose we did that at 6,800 kilowatt hours per ton. Translate that into costs. That's about penny a joule for energy from ammonia produced that way, whereas today's gasoline is about 3 cents per joule. Remember joules a watt second? Then I looked at the California state analysis of their gasoline costs, and more than half of them are from the crude oil that goes into the gasoline. So I say, well, that's the energy content. The taxes and distribution, refining, those are all going to be the same. Suppose we used ammonia. What might we get? Well, we might get a third of that cost because it's only 1 cent instead of 3 per per joule, we could reduce the cost of the gasoline equivalent. Now, I'm making the leap of faith that engineers can create refineries that can produce this kind of ammonia fuel as efficiently as do today's petroleum refineries. Well, suppose you don't like the hydrogen and you don't like ammonia. We have to go back to carbon, but we don't want to take it out of the ground. What are the sources for carbon that do not pollute the atmosphere more? We like to make these kinds of chemicals. One is the project called Green Freedom, which was done at Sandia, never done, just designed. And the idea was to use a liquid in the cooling tower of a nuclear power plant that was saturated with sodium bicarbonate. When sodium bicarbonate is heated, it exudes CO2. That's how baking powder works in your kitchen. So you can capture that CO2. A guy named Jim Holm in the thoriumapplications.com website has another scheme using the cooling canals of a nuclear power plant, such as the one in Florida, to do the same kind of thing. So that's a potential way to do that. Of course, we can also do that by getting carbon from agriculture. Now, farming produces about 3 tons of dry biomass per acre per year, no matter whether it's switchgrass or corn or trees. And about half of that is carbon. But let's not burn it. Let's not do what the ethanol people do. Let's use the carbon in it to be the carbon that's going to go into one of those hydrocarbon fuels. We'll add hydrogen to it in order to create the fuels. We'll get about a 3-to-1 fuel improvement ratio doing that. About 1.7 tons of biomass would yield a ton of fuel. U.S. farmland is about 1 billion acres. We use already about 1 billion tons of fuel a year. We'd have to reduce that a lot in order to be able to satisfy our fuel appetite in the U.S. But on the other hand, if we didn't burn coal, we wouldn't have so much diesel fuel burned in trains. Half of the train traffic in the United States is hauling coal to power plants. We can electrify the rest of the railroads. We can do better. So we might be able to live with that source. Cattle dung is burned in a lot of countries for fuel, but it's a source of carbon. Same thing. World cattle dung is about 2.5 gigatons per year. That could make a lot of fuel if we could collect it and burn it. So there are other sources of waste hydrocarbons that we can consider as sources to make carbonaceous fuels. In summary, I say, try and develop this technology. And I advocate public domain ownership of the R&D of the first 5 years. Produce and export it. Zero out coal plant CO2 emissions. Synthesize climate neutral fuels. Avoid the contentious carbon taxes that mean that meetings such as Durban never succeed. Improve world prosperity by raising people out of energy poverty and that check the overpopulation growth. Reduce the radiotoxic waste from the existing things and use the world fissile stocks of excess weapons grade plutonium and U-235 and so on to help start up these reactors. Use inexhaustible thorium fuel, which is available in all nations, giving energy security, and create a walk-away safe reactor. Again, cost is the important thing. We need to have energy cheaper than coal. The designers of that reactor are probably in this room. So I ask of you to remember there's a tipping point here. If you have energy cheaper than coal, we can solve that world climate and population problem because it will be in the economic self-interest of 250 nations to buy those cheaper power sources rather than burning coal. If we don't make that and people find that they want to continue burning coal, then we'll have the scenario that was outlined by Dennis Meadows and the Club of Rome.
Thank you, Robert. This is Bob Savinsky from the University of Huddersfield. Unless I missed it in your talk, you didn't give a comparison of the cost of electricity from a molten salt reactor with that of conventional nuclear, nor a comparison with the cost of using thorium, for example, in more conventional nuclear reactors. I just wondered if you could comment on that.
We know the capital cost of a conventional reactor is about $5 per watt today, and the cost of fuel is trivial. So a typical uranium reactor today is competitive with coal, hydro, natural gas, about 5 or 6 cents a kilowatt hour. So it is a valid and reasonable source of power today. Thorium has been used to sort of enhance the lifetime of the fuel rods in previous reactors, and I see no reason why that wouldn't work as well.
I was looking at the cost for a lifter reactor, for a thermal molten salt reactor. As far as I'm aware, that really breaks down into the cost of building the reactor and building the reprocessing. And I was wondering if you had any figures of the ratio of those costs.
The best I could do was to find those examples I showed you. I don't think we can get a really good cost estimate until we have a really good design, to be honest. I think, however, that the single fluid reactor is bound to be a lot less expensive, and it's probably going to be the first to market.
That was a fascinating talk. It's Bryony here at the front. I would just say, though, that I think the second half of your presentation gave me great hope and was really fascinating. The first half, where you talk about the costs of renewables, I don't see this as a competition between renewables and nuclear. I think they can be complementary and work together. And the reason we're paying a high cost per kilowatt hour at the moment is because we want to exactly do what you've suggested and have that learning curve development. More deployment, costs come down, and you find different ways of integrating it into the grid. So I just would say, let's try and create a big tent here. Let's try and work together. All low carbon sources should work together, and we've got to beat coal. I think the future for renewables is very bright, and some of my question, I suppose, is, what do you think about the integration of intermittent sources of renewable energy with storage systems such as heat stores, thermal stores being used in homes and businesses, which is what they're doing in Denmark now?
We should allow renewables to try to compete in this market, but we shouldn't hide from the public the true cost of what's being paid. So in the long run, we need to cut down the subsidies, particularly for ongoing production costs of electricity. The holy grail for renewables is to be able to store the electric power one day and use it the next. And it's very expensive. The only practical ways, and they're not very practical, that I've seen that work at all, are pumped hydro and underground compressed air storage. But both of these lose some energy. The costs of batteries for storing basically move the decimal point over 1 when you're trying to look at the cost of electric power. Arrays of windmills can sometimes back each other up because when the wind lulls in one place, it may peak in another. But generally, the storms are correlated, and so the wind does need to have backup from fossil fuel plants. Measurements were taken in Ireland where they were expecting a 12% reduction in CO2 from the wind farm's presence, but in reality, they only observed a 3% reduction. The reason is that the fossil fuels that had to back them up had generators that had to start and stop, and that causes more fuel to be consumed. By analogy, in the US, we have cars that have mileages of, say, 20 miles per gallon for city driving and 30 miles per gallon for highway driving. It takes more energy to start and stop the car, just as it takes more fossil fuel energy to stop and start the fossil fuel generation plants.
Okay, thanks.